So far we have completed representing each and every node individual type, as well as we have also uh, written the class for representing singly linked list in our programmatic implementation, right? Now we have everything in place. Now let's get on with implementing the very first functionality, that is push functionality on a singly linked list. So generally what exactly this push functionality does is it will basically take the new value from the user and it will basically try to create a new node of type node that we have defined, and it will make sure that it is inserting that node at the end of the singly linked list. That means the end is exactly at the tail node, right? Because the tail value inside the singly linked list basically represents the very last node that we have, and obviously we have the tail node access as well inside the singly linked list representation that we are maintaining. So as part of the push operation, whatever the new node object that we create with the value that we take from the user, and it will make sure that it is adding that new node at the end of the singly linked list. But remember that, because we are adding a new node at the end of the singly linked list, whatever the tail node that we had previously, right, that will no longer be the new tail node. Whatever the new node that we have added will become the new tail node of the singly linked list. That is something that you have to remember. That means whatever the tail node that we are maintaining inside our singly linked list representation, right, we have to update it with the newly added node. Okay, so that is the simple definition. So what exactly we will do, we will take the value from the user and we will create the new node object of type node that we have defined, and we will make sure that we are adding it at the end of the singly linked list. So what all are the different cases that could come while implementing the push operation, right? So basically remember that, whenever you are adding a new value or new node into the singly linked list, right, there could be two scenarios. The first scenario is to check if the singly linked list is empty, and the second check would be to check if the singly linked list is not empty. Whereas when you are trying to remove the value from the singly linked list, right, then there will be three scenarios. First scenario is basically the singly linked list can be empty, and the second scenario is basically where we have only one node, and the third scenario is basically where we have more than one node inside the singly linked list representation. Since here we are introducing a new value onto the singly linked list, right, so obviously the first case would be to check if the singly linked list is empty, right? Obviously when the singly linked list is empty, whatever the head node and tail node that we are maintaining, right, in the case of Java or JavaScript representation, we are maintaining null value in it. Otherwise, if we are trying to do it Python based implementation, right, in that case we are storing none in it. In both head and tail we have null. In the case of Python implementation we have none. Similarly inside the length we are having 0. So whatever the new value that I am adding into the singly linked list, that will be the only node that will be present inside the singly linked list, right? That means whatever the node that we have added will become the head node as well as the tail node. So we have to make sure that we are updating the head with the new node that we have added. Similarly, tail node also we have to update it with the new node that we are adding, because we have only one node in the singly linked list. That means that itself is the head node and tail node. That's why inside the head value and the tail value we are maintaining, we have to make sure that the reference of new node is getting updated inside that. Similarly, since we are adding a new value into the singly linked list, we need to increment the length by length plus 1. Okay, so that is the first scenario where head and tail were not there. That means the singly linked list is empty. Now let's try to understand the second scenario where we have a non-empty singly linked list. So non-empty singly linked list case is what we have here, right? Obviously here we have some number of nodes already available inside the singly linked list, and we have the head node and we have also have the tail node. So each and every node has some value in it. Let's say 10, let's say k, let's say true or something like that. Now let's just say I want to add or I want to push the value, let's say code, onto the singly linked list. So what I will do is, we already have the reference of the head tail node, right? So from the tail node, the existing next pointer in the tail is, at this point of time it is null if you are doing Java or JavaScript based implementation, if it is none if you are following the Python based implementation. So here we will basically create a object, node object with the value code, and we basically update the reference of the existing tails next to newly created node. That means in the existing tail node we have the reference of the newly created node as well. So we have adjusted the next pointer of the existing tail, and obviously the next on the newly added node is, obviously it is empty. Now this, whatever the true node that was there, will no longer be the tail node of the singly linked list, right? So what we have to do, we have to update the tail node to the newly added node, that is code. That means whatever the tail reference that we are maintaining inside the singly linked list, right, it should be updated with the new node that we are adding. In this case we will not do anything with the head because we had certain number of values inside the singly linked list. That means head is somewhere but the tail is somewhere, and to that tail node we are adding a new node as part of the push functionality. So we will not do any changes to the head node, we will simply update the tail node with the newly added node, and we will also increment the length by 1. Okay, in this way we are keeping consistency in the tail node because we are adding a new value into the singly linked list after the end, and we are adding a new node into the singly linked list, right? That's why we are incrementing the length by 1. So that is how we are maintaining the consistency across the variables we are maintaining inside the singly linked list representation. Okay, now according to the algorithm that we have discussed, right, for various cases on a push operation, now let's try to write the pseudo code for the same. So inside the pseudo code, what exactly we are doing, we basically define a function called push function, and this function will basically take the new value from the user. So for as part of the first step, we have already defined the node class, right? So we basically create the node object with the value that user has passed, be it empty singly linked list, be it non-empty singly linked list, we have to have the object of node first. Based on that, based on whether the singly linked list is empty or based on the singly linked list is not empty, we will try to perform the operation, right? So after creating the object, what we will do is we will check if singly linked list is empty. How we will check? If you are doing Java or JavaScript implementation, right, inside the head, when we created the object of singly linked list, we have assigned null, and inside the tail also we have assigned null, and inside the length we have assigned 0. If you are following Python based implementation, right, inside the head node, null equivalent is none, right? So we have defined head with none. Similarly, we have defined tail also with none, and length we are maintaining 0. Now if the singly linked list is empty, in the case of Java and JavaScript implementations, head and tail will be pointing to null and the length of singly linked list will be 0. So based on that, we will be able to decide if the singly linked list is empty or not. Now anyway, that algorithm I have already explained, just that I am trying to give much more context here. So if at all, if the singly linked list is empty, right, whatever the new node object that we have created will be the head node. So head node, we will update it with the new node object. Similarly, since that is the only one node, we will make sure that tail node also is getting updated with the new node object that we have created. And after that, we have to increment the length by 1. Increment length by 1. In the end, we will simply return the node that we have added. That is, whatever the new node object that we have created, we will return that. So this is the case where the singly linked list is empty. If at all, if the singly linked list is not empty, right, that means it is not empty. In the case of non-empty singly linked list, we already had the reference of the tail node inside the singly linked list containing some number of values. So inside the tail node, obviously the next reference was empty. So we have to make sure that since we are adding a new node, this node's reference should be present as part of the existing tail node, right? So first we will read the tail node. Okay, so in this tail node we will basically update the next to new node. Okay, that means we are adding this object reference into the existing tail node. After updating, we have successfully added the new node into the singly linked list, but the tail node is still pointing to the old last node that we have inside the singly linked list. So the tail node should be updated to the very last node we have in the singly linked list. To do that, what we will do is we will simply update the tail node to the new node object that we have added. Similarly, in this case also, we have to increment the length by 1. In the end, we will simply return new node object. Okay, so this is the pseudocode for implementing the push functionality on a singly linked list. So remember that there will be two cases. One will be empty singly linked list and the other will be non-empty singly linked list. Okay, so that is how we perform the push functionality, and let's go ahead and let's try to implement it programmatically as well. So here let me just define one function called push function, but ultimately in the end, after adding the node with the value whatever that user wants to add into the singly linked list, we need to return that specific node object that we are adding with whatever the value that user has passed. So let me just define the return type of the value as node of type t, whatever we have defined here. Now let me just name the function as push, and it will basically take the value of type whatever the values that you want to store. So the type of the values that you can store are also similar to what object you have created while initializing the singly linked list class. So here t represent the same type of values needs to be passed for this push function as well. Okay, now whenever we are introducing new value into the singly linked list, right, obviously there will be two scenarios. The first scenario is obviously you are trying to add it onto a empty singly linked list, and the second scenario is obviously adding new value at the end of the singly linked list when the singly linked list is not empty. So here whatever the values that we are keeping track, right, head, tail and length are the values that we are keeping track of. When the singly linked list is empty, head is null, tail is null and length is 0. So based on these values we will be able to say if the singly linked list is empty or not. If this condition is not matching, obviously the singly linked list is not empty. So ultimately, as part of this push function, we need to add the new node with this value at the end of the singly linked list. That means we already have the tail node. After this tail node, we need to add the new node. So whatever the node that we are adding, right, that node will become the tail node of the singly linked list, because that will be the last node that we will have after introducing that new node. So to implement this push functionality in both scenarios, like I've mentioned previously, let's write the logic quickly. Now, first of all, even if the singly linked list is empty or not empty, ultimately we would be needing the node object with this value, right? So let's just create that first. So node of type t, let's just say new node equal to new node of, here also we need to pass the type, and the object node class constructor basically requires a value, right? Let's just pass the value whatever that user has passed. So we have the new node object ready. Now what we need to do, we need to honor the two cases where the singly linked list is empty or the singly linked list is not empty. So to check if the singly linked list is empty, let me just depend upon the length. If the length of the singly linked list that we have is 0, that means that it is empty. What we can do immediately, so whatever the node that we are adding will be the first node as well as the last node. So what we can do is we can simply update the head node, whatever we have on the singly linked list to the new node that we have created, and the tail node also will be the same node, because whatever the node that we are adding, it itself is the only node. That means head and tail, because that is the first node and that is the last node. So head and tail both should be updated to new node object that we have added. Along with this, since we are introducing one node into the singly linked list, what we need to do is we need to increment the length by 1. So this dot length equal to length plus 1. Okay, so this is the logic when the singly linked list is empty. But what if the singly linked list is not empty? In this case, what we need to do, we already have the access of the current last node in the tail value. Now we need to add the new value after the tail node, right? So whatever the value that we want to add will be the next of the current tail node. So for that addition, we can simply read the tail node first. On this tail, this is of type node, right? On this node we have the value and we have the reference of the next node. So we can immediately update the next of that node with the new node object that we have created. See, if you remember, I have mentioned while defining the node class, I will explain you how we will assign the next node with appropriate node while implementing the certain features on the singly linked list, right? If you observe here, the existing tail nodes next is right now was pointing to null because there were no more nodes after the tail node. Since we want to add one more node after it, we have updated the next of the current tail node to new node that we have added. Again, this new node is the last node right now after adding the new value, right? So we need to update the tail node of the singly linked list to new node that we have added. After this, since we have introduced one value into the singly linked list, we can simply update the length by 1 as well. If you observe here, these two statements are common in both if condition and else condition. So you can write the common logic as well outside this else block, which is common for both, if condition and else condition. That is also absolutely fine, but I feel this gives much more readability. That's the reason why I'm putting it here. Okay, anyway, once we add the value into the singly linked list, ultimately in the end we need to return the object that we have added, right, which is nothing but the new node. So we can simply return new node object like this. Okay, so that is the simple implementation of the push operation, honoring when the singly linked list is empty and the singly linked list is non-empty. Okay, now that we have implemented this, let's quickly call this function and let's just try to see if we are able to add the values or not. So here let me just comment out this second singly linked list part here, and here let me just add SLL dot, we have the push, right, and we are mentioning that the singly linked list that we have defined is of type integer. As a result, if you look at the intelligence that we are getting from Visual Studio Code, the push function is also taking integer value only. So we need to pass the integer value here. If you try to pass any other type of values, we will basically get the errors. Okay, now here before adding the values, before pushing the value, we are printing the head and tail, and let's just print after pushing the value 10 also into the singly linked list. Obviously before push, the singly linked list is empty, right? So we will see null, null and 0 for length, and after adding, since this is the only node, as a result it itself will be the head node and it itself will be the tail node, and length will be 1. So if I execute this, I can simply run code. See, here in the beginning we have got null, null, 0, and after that we have got 10, 10 and 1. That is because in the print statement in the else blocks, okay, we have not added any helper text here. We can do head node just like how we have in the if condition. Similarly, here also we can add tail node. Okay, so this will simply add some text before the 1010 whatever we are printing on the screen. Okay, so head is null, and here after adding the value 10 into the singly linked list, head is 10 and tail is 10, and the number of values we have in the singly linked list is 1. Now let's just add one more value into the singly linked list. Let's just say this time I want to add -10. So if I execute this now, head should be 10, and after 10 we are adding -10, right? So -10 is the last node, which is nothing but the tail node. So that is what we should see on the log as well. So if you see here, head node is at 10, which is the first node, which is 10 that we have added first, and the tail node is -10, and the number of values we have on the singly linked list is 2. Similarly, let's just say here, instead of first adding 10, let's just say I want to add 0. So 0 is something that we are adding first into the singly linked list, right? So as a result, head is 10, after 10, sorry, head is 0, after 0 we have added 10, and from 10 the last value is -10. As a result, the tail is -10, head is 0, and the number of values we have in the singly linked list are 3. So that is what we should see on the console. See, head is 0, tail is -10, and length is 3. So whatever the values that we are adding into the singly linked list are getting added perfectly at the end of the singly linked list, honoring the both empty singly linked list and non-empty singly linked list as well. If at all, if you want to create a singly linked list which basically stores the string values also, you can do the same thing. That is absolutely fine. For one functionality, let me just show you, so that going forward we can only stick to this singly linked list integer type objects validation for that specific function that we are writing. Using this reference, you can validate the same thing as well. And here, if you see here, the push function is taking string values only. Why? Because whatever the singly linked list object that we have created, we are mentioning that it will only contain string values. Okay, so that is the reason why it is taking only string values. Let's just say I want to add one value, codingpal.r, and after that let's just say I want to push one more string called test. Okay, so since we have added codingpal.r first, this will be the head node and the tail node will be test. So if we simply add this print head and tail and length after that, you will be able to see the same thing as well. Passing argument to parameter. Okay, here I just need to add SLL2. It is not SLL. Okay, run code. If you observe here, head is codingpal.r and the tail is test, and the number of values we have on the SLL2 is 2, which are codingpal.r and test. Okay, I hope you understood. This is how we implement the push functionality, which basically adds the new value at the end of the singly linked list, honoring all the scenarios like we discussed. Okay, so that's it for this push functionality. In the next video, now that we have added one value at the end, let's try to understand how can we remove the value from the end, which is nothing but pop operation on the singly linked list. Alright, now we have written the programmatic implementation of push functionality as well, right? Now let's just try to understand the time complexity and space complexity involved in performing the push functionality on a singly linked list. To handle the both scenarios, even if we have n number of nodes in the singly linked list, or even if the singly linked list is empty, what exactly we are doing? First step, we are basically creating the object of the new node with the value that user has passed, right? So obviously for that creation of object, we will not take more than 1 unit of time. Similarly, in the case where we don't have the nodes at all inside the singly linked list, right? Exactly, we are simply updating the head node and tail node with the new node that we are creating. Since these are simple assignment operations, and incrementing the length also is a simple assignment operation, right? These operations will take 1 unit of time itself. As a result, when we don't have any nodes inside the singly linked list, the time complexity will be order of 1 only. Similarly, even if we take the case where we have certain number of nodes inside the singly linked list, that means the singly linked list is not empty, right? In that case also, we are maintaining the reference of the tail node in our singly linked list representation. That means inside that class that we are maintaining for singly linked list, we can directly read the tail node. That read operation is obviously is going to take 1 unit of time itself, and after that we are updating the next reference of the current tail node with the new node that we are adding. So obviously this is also a simple assignment operation, and it will take only constant amount of time. In the end, just like how we handled updated the tail reference and incremented the length by 1, right? Then these are also simple assignment operations, so these will also take constant amount of time. So as a result, even if you take the case where we have certain number of nodes available inside the singly linked list, the time complexity will be order of 1 only. And if you take the space complexity, obviously the only space that we are consuming is basically to create the new node with the value that user has passed. Obviously we can't skip that node object creation, right? And we won't consider that as a memory consumed by the algorithm that we are using for performing the push operation. So obviously the memory that is consumed by creation of node object will also be constant. And if you take the case where we don't have any nodes inside the singly linked list, we are simply updating the reference of the head that we have already have inside the singly linked list and tail with the new node. So these will obviously simple assignment operations, and they will not consume any more memory internally, right? As a result, overall memory consumption in the case where the singly linked list is empty, right, it will be constant. That is, it is order of 1 only. Similarly, if you take the case where the singly linked list is not empty also, we are not consuming any memory, we are simply performing the assignment operations, and these assignment operations will not take more than a unit of memory, right? That's why in this case also the space complexity will still remain order of 1 only. Okay, so that is all with respect to implementing the push functionality on a singly linked list. In the next video, let's talk about the pop functionality on a singly linked list, where we try to delete the very last node we have inside the singly linked list.